Hello, in this video we'll focus on kinship and kin selection. And we'll get right started by popping over to my PowerPoint. Okay, so in our last video we focused on how cooperative behaviors could evolve. And one way in which cooperative behaviors could evolve I called kin selection. And I gave you this example of how scrub jays are likely to, as adults for a couple of years, are likely to, instead of breeding themselves, help their parents out by raising siblings, if you will, by helping to raise siblings. And we might wonder, how did this evolve? Why is it that scrub jays would forego their own reproduction or potential reproduction to help their parents raise other individuals, their siblings, at the nest? Kinship theory and kin selection can help us understand this. And that's why we're going to take a look at it today. So kinship theory, or and sometimes we call this inclusive fitness theory, and tests of it, conflict with animals, and kin recognition. This is where we're headed in this video. And there's just this statement made by Haldane that you will understand probably as we move through kin selection. I would risk my life to save 2 of my brothers or 8 of my cousins. There are a lot of questions that can be addressed by kinship theory, and that's always a mark of a good theory. If you can use it to predict and answer questions that you have, then it's probably a good theory. So look at all these different examples. We could add in there, why do scrub jays, reproductively mature scrub jays, forego their own reproduction to help at their parents' nest? Why do female Belding's ground squirrels emit more alarm calls than males? Despite high homicide rates, humans rarely kill their genetic relatives. Why? Why do male lions put up with being in a coalition of males that defends a pride but rarely gets to mate? Is there ever conflict between a parent and an offspring? Why do siblings fight? All of these questions can be addressed by this bigger theory called kinship theory. Kinship theory, or inclusive fitness, was identified and developed in the 1960s by a researcher named Hamilton. And in this research, he tied together, or in this theory, he ties together genetic relatedness, or kinship, with the evolution of cooperative behavior. Remember, we're thinking about how could kin selection lead to cooperative behavior in animals. So we need to sort this all out. So first of all, what is kinship theory? And I don't really have an answer here. First, I've got written that, sure enough, kinship is a powerful selective force. Relatedness is a powerful selective force that shapes social behavior in animals. So relatedness can shape social behavior. And how? Well, we need to step back and think about the definition of fitness. When we're focused on natural selection, we said that there should be selection for behaviors, right, or traits that enhance or improve an individual's ability to survive and reproduce, leaving behind offspring in the next generation. So behaviors that contribute to one's direct fitness are going to be selected for. Inclusive fitness is a little broader than direct fitness. Sometimes we call inclusive fitness indirect fitness, but inclusive fitness actually is a measure of an individual's total fitness. And by fitness, we mean the contribution an individual makes to the next generation, the genetic contribution. How many offspring does it leave behind? Oh, in inclusive fitness, total fitness includes how many offspring it has. That would be the direct fitness component. And the contribution it makes to the reproductive success of its relatives. So, we have to write that down a minute. So, let's see. In inclusive fitness, we could say it's a measure of an individual's total fitness okay? That includes how many offspring it has. So it includes the number of offspring that it produces, right? Plus the reproductive success of its genetic relatives. Reproductive success of genetic relatives. Of relatives. Okay? Okay. So if we're talking about scrub jays, we would say scrub jay's inclusive fitness would include all of the offspring it produces plus all of the offspring it helps to raise, all of the relatives it helps to raise. And if a behavioral trait contributes to an animal's inclusive fitness, then it should be selected for. That's kin selection. Kin selection is essentially the selection of traits that raise one's inclusive fitness, including direct and indirect fitness benefits. All right? Okay, so let's think about genetic relatedness. We have to understand that concept in order to understand kin selection, measuring relatedness, if you will. Okay? So in order to measure relatedness, so some of us are more closely related than others. How close are we genetically related to our parents or to our siblings or to our cousins or to our second cousins? Can we calculate this? Can we come up with some measure to do that? Yeah, absolutely. We can calculate on average the percent of genes that we share by common descent. And that's called a coefficient of relatedness, the percent of genes that two individuals share by common descent. What percent of my genes do I share with my sister Cheryl? What percent of my genes do I share with my son Ben? You know, we can calculate this on average. So, and we can ask this question in a variety of ways. One of them is, how likely are you and your full sibling to inherit an allele that is identical by descent? All right. This is essentially asking the same question as, about what percent of your genes do you share with your full sibling? Well, how do you calculate that? The coefficient of relatedness, big R, XY are the individuals, is equal to, and here we've got a term that you might not be super familiar with, the sum of, that's that funny E, right? The sum of 1/2 raised to the power n, where n is the length of the path. Where n is the length of the path between two individuals, or between individuals, okay? So my question then is, how likely are you to inherit, how likely are you and your full sibling to inherit an allele that is identical by descent? Let's determine the coefficient of relatedness. The coefficient of relatedness would equal 1/2 raised to the power n times the total number of paths in the system. So let's look at this pedigree a minute to help us understand it. In the pedigree, I've got, a dad and a mom, and they have 3 kids, a male, a female, and a female, all right? Maybe I'm interested in asking, what is the coefficient of relatedness between a male and his full sibling who shares a mom and a dad, right? Well, to calculate this, we think of what is the sum for each pathway of 1/2 times the length of the path. So what's happening here is I need to think about how are these two individuals connected? Well, their dad connects these two individuals, right? Each of them inherits some genetic material from their dad. So that's one pathway that they're connected through their dad. What is the length of the path? Well, the length of the path is the number of arrows between them, between this male and this female. There are 2 arrows, right, connecting them. So the length of the path is 2. That's the first path. Well, is there another path by which they're related, by which they could share or could inherit an identical allele by descent? Yeah, absolutely, from their mom. And their mom's path length is also 2. So for mom's pathway, we would have 1/2 raised to the power 2 as well. So the total answer would be 1/2 raised to the power 2. 1/2 times 1/2 is 1/4, plus 1/4 equals 1/2. The coefficient of relatedness between two full siblings is 1/2. Big R equals 1/2. Or you could say the relatedness, or the coefficient of relatedness is equal to 0.5, right? On average, we share 50% of our genes, and you probably knew this, with our full siblings. We get, on average, 1/4 of those genes from our dad and 1/4 of those genes from our mom, all right? So we are about 50% related to our siblings. That's a pretty high R value. What about half siblings? So here I've got a pedigree between that has, let's see, Mike and Jane have one son here, but Jane had a daughter through another, with another man. What is the coefficient of relatedness between these two half siblings, if you will? Well, we'd say, let's find all the pathways by which they could share genetic material. That would be only through their mom, through Jane, right? And the pathway is 2 arrows long, or 2 units long. So 1/2 raised to the power 2 is 1/4. The coefficient of relatedness for half siblings is 1/4. They share about 25% of their genes. How likely are you and your cousin to inherit an allele that is identical by descent? So now I've got a more complicated pedigree going on here. I've got grandparents up here in the first generation, and they had, a number of children, 3 children, who got married and had some kids. And now we're dealing with some cousins in the 3rd generation. Let's look at these 2 girl cousins. How much genetic material do they share on average? What is the coefficient of relatedness between them? Well, we have to think about all the paths by which they could inherit an identical gene, and then we have to make our calculation. Let's look at the paths. Well, let's see. They could get identical genetic material from their grandpa or from their grandma, as far as I'm concerned. So their grandpa would be like, okay, who could donate to this daughter, who could donate to her daughter, okay? And a grandpa could donate to his son, who could donate to this cousin daughter, right? That's one pathway. Otherwise, that's one pathway. So let's see, the sum for that pathway would be 1/2. How many arrows long is that? 1, 2, 3, 4, raised to the power 4. Plus, they could also inherit alleles by descent through their grandma, right? And that pathway length is going to obviously be similar in size for this one. So through grandma, they could have, let's see, I don't know what 1/2 raised to the power 4 is. 1/2 times 1/2 times 1/2 times 1/2. That's 2 times 2 times 2 times 2. 2, 4, 8, 16. 1/16 from their grandpa and 1/16 from their grandma, which is 2/16 or 1/8. So the coefficient of relatedness is 1/8, or R is equal to 0.125, 12.5%, basically. They share on average 12.5% of their genes with each other. This coefficient of relatedness is important when we start thinking about kin selection. Okay? So in the next video, we'll talk about kin selection, but remembering how to understand relatedness is super useful. Okay. Let me get out of here, if I can.